So far, we've been working with the data in raw vector form, the coordinates of the points and the paths they create. But that's not what we humans see when we look at the drawings. We see the pixels. And some features can be calculated more meaningful if using those. Like, these drawings look the same, but their vector representation is very different. And it would be quite strange if they would not be classified as the same thing, wouldn't it? If you've never worked with images, you can watch this video where Green Radu explains how to make an image recognizer that works with the camera. I think it's a good watch, especially now that you have a good understanding of machine learning already. Now, I won't teach you any sophisticated image processing techniques, but I want to set you up just in case you want to experiment more. There are a bunch of things that can be tried out with this new approach. Self-study them, ask me questions in the comments or on Discord, and we'll try to figure things out. Get it? Figure? Because images are... No.
Gonna code, debug, and have fun. Coding with Radu. Coding with Radu. Gonna prototype and design. Coding with Radu. Coding with Radu. Let's code now.
Let me show you how we can access the pixels from the canvas. I'm going to do this in the console here and type sketchpad CTX, getting the context of this sketchpad that we're drawing on, and get image data from 0, 0, which is the top left corner, using the sketchpad canvas width and the sketchpad canvas height. So I want to get all of this information. And if we press enter, we get this, which is containing some information about the color space, the width and height, 400 by 400, and this really long data array here. Now, this data array is going to be filled with the zeros pretty much, because that's what is drawn on the canvas now. Everything is actually transparent black. This stands for red, green, blue, alpha of the first pixel in the top left corner on the canvas. And this is the pixel on the right of that. So red, green, blue, alpha, red, green, blue, alpha, and so on. If I'm going to draw a line here on the canvas and run the same code here again, you can see zeros here, but at some point we start getting some values. And these are the values from this line that I drew here, and they only appear as alpha values because the lines are black. Actually, they are here inverted because of the styling, but basically anything with an alpha is a pixel that is lighting up. So that's what we want to extract from here, really. We don't care about colors. We just want to know which pixels are visible and which not. So if I'm gonna bring this code back here again, we can filter this to take just the fourth item in the array. Every fourth item in the array using filter on the data and taking the value and the index. So here we're gonna filter using this index if modulo 4 is equal to 3. And this gives us that, just the alpha values, and they are 160,000, so this is 400 times 400. A matrix written in linear form, pretty much. So let me close this console and write the code to extract these pixels in our feature functions. I'm going to go in Common, Feature Functions, and here below the roundness feature, I'm going to implement a function to get these pixels. It won't be a single number as an output, it will be all the pixels. It's not a feature yet, but eventually we'll use it as a feature as well. You'll see. And I'm going to write it here in the feature functions for now. So let's write here get pixels, and given the paths, now by default we used this 400 by 400 pixel canvas all the time. I'm going to set the size here equal to 400, but we can set the parameter here to get the pixels from a smaller canvas if necessary. Let's first define our canvas, and I'm using let here and setting it to null because now I'm going to do a trick. I'm going to try to initialize the canvas for the web by asking the document to create a canvas element like this, and then setting its width to the size and its height to the size, like so. But if this fails, it probably means that we are doing this in a node, and I'm going to catch an error. I'm not going to worry too much about what the error is, because in our environment, this can only be the reason why it doesn't work, that we're trying it on node. So this code here is for node, and here we have to require the create canvas function from node modules canvas, where the canvas was installed. And then our canvas can be initialized with create canvas size and size, like this. Now the code should work both on web and inside of node. And we can now get a reference to the canvas context, like so, and draw these given paths here on this new canvas. We then get the image data. From the whole canvas, and take out just the alpha values that we're interested in. So I'm just going to return directly image data dot filter value index, and then index modulo 4 when it's equal to 3. So every fourth element will be returned. Now we're drawing here, and we haven't included that file here yet, so I'm just going to do that real quick. Draw, like so. And now let's test our code in the dataset generator again. I'm going to go here in node dataset generator, and we need to include the feature functions here. So feature functions and feature functions. And let's go down where we are generating the image. And we don't need this fancy stuff anymore, because this new visualization will be just me writing some text on the images, how many pixels are visible. So let's first access these pixels using our newly created function, and let's store the number of pixels in a variable which we're going to call complexity, because I'm eventually going to make a feature from this, and complexity just means the more pixels, the more complex it is. So let's say complexity is, and we count now how many values are non-zero. These are just the alpha values, remember that. So if they are visible, they will be counted. And then let's just draw some text, this complexity value, and let's use blue color. Now this draw text doesn't exist, so let's save this file and go here to draw.js. We can draw paths, but we can't draw text just yet. So we need to implement a function for this, given the context and the text. And the color, we set it to blue, but let's give this one a default color as well. And now the location by default will be 0, 0, where we want the text to be in the top left corner. And Let's set a relatively large size because we are just printing there those small thumbnails in the viewer. The text should be quite big. Now, this function is going to first set the font, and I want it bold. Let's concatenate here the size, and I will use Courier font. Because I want the text to be in the screen, I want the baseline to be on the top, because if 0, 0 coordinate is used, otherwise the text would just be over that and we wouldn't see it. And I'm going to put here text baseline stop. And let's set the fill style to the color and fill the text at this location. I'm just spreading the array into the two X and Y components. And that's it. Let's save this and open a terminal. Make sure we are in the node folder. And let's generate our dataset once again. And while it's doing that, we can quickly check what happens here in dataset image. And this is a number that probably works, meaning it's the number of visible pixels here. Maybe it's okay. We'll see later when we can visualize them in the app. But while it's doing this, I'm actually going to implement the complexity function that I mentioned. So let's go to our feature functions here below the new function we just created. And the complexity function is going to be just get complexity from the paths, and it's going to return this one number. So first thing that happens is we extract these pixels. And now we're going to count how many of them are visible. Like so. And we can add this new feature here. And get complexity like so. Now we're dealing with this 5-dimensional feature vector. And I don't really know how good this feature is going to be. I don't really have high hopes. I just want to teach you how to work with pixels. And then it's up to you. You can look online, find some help how to do image processing if you're curious, but I won't get into that. Now this is done. Let's also extract the features. And this is probably going to take some time now because doing this pixel manipulation is time consuming. Each image is 400 times 400, so a lot of calculations. Let's add here also this kind of progress indicator. So I'm going to go to feature extractor, and this for loop here where we are looping through the samples, let's rewrite it using a classical for loop, looping through all the samples like that. And let's here initialize the sample as samples of I. And at the bottom here, let's print the progress using our utility function I and samples length -1 for 100%. Now, next time we run this code, we will know how long it takes. At the moment, I have no idea, so I just have to be patient. And it's done. Let's now run the evaluation. There is some improvement. It jumped to 66.13 here. And now this decision boundary plot is going to use all of the features because we implemented in a general way last time. But I don't really care about this decision boundary plot anymore. It's not very usable as it is when more than 2 dimensions. So we're done. Let's refresh the page. And this is what we get. We see now the numbers here. And I think they're proper. this is a very small value here, 1000 something, when most of them have several thousand, and you can see just a few pixels showing up for this small pencil. I think that this is correct. But thinking about it, it's kind of unfair to say that this is less complex than this, because they kind of look the same. If we talk about the feature meaning complexity, maybe we should scale these items so they fill the whole canvas, and then count how many pixels are lighting up. Let's try to do that. I'm gonna teach you a little bit of image processing anyway. So let's just scale these and stretch them to fill the whole canvas and see if this feature improves or not. But I won't insist more than that. In feature functions, where we extract our pixels here, I'm going to pass another parameter to the function saying if we want to expand or not, so that the drawn image fills the entire canvas. And if it's set to true, which will be the case by default, then we go here before drawing the paths and rescale these paths somehow. We check if we need to expand, and if we do, I'm going to take the bounds first, the minimum, maximum on the X and Y. So let's take out the points by flattening the paths. And these bounds will be an object with left equal to the minimum point, only looking at this X coordinates, the first coordinate here. So I'm going to copy this like so for the right with the maximum here. And let's copy both of these for the top and the bottom. Now, these will be 1 here because we're using the second dimension. We are now going to remap these points and generate some new paths with remapped points. So let's write here new paths, and this is going to be an empty array. And we're going to loop through the paths, path by path. And now we're going to generate new points from the path's current points. So these will be in this variable, and we'll use the map function where we remap each point P to be a new two-dimensional array. The first will be remapping using inverse slurp between left and right using P of 0. And this is going to give us a value between 0 and 1, depending how far from left to right we are. So we have to scale this also by the size of our canvas. Now I'm going to copy this again here, and this will be between top and bottom using the first dimension here. Now we need to push these new points into our new paths every time we create them. And finally, we can draw here the new paths on the canvas. So new paths, like so. And this will go in the else clause. So here we have else. We do that because in this case, we don't want to expand anything. Now, if we open our terminal and regenerate our data, if we look here, we will start to see that the values are different than before. But I would also like to visualize what we did exactly. So while it's running, I'm going to redo the visualization part in this dataset generator here, and I'm going to show the new image that we get after expanding them. So here, after we have our pixels, I'm going to figure out the size. They are going to be a square canvas always, so I just take the square root of these pixels, length, and then let's get the image data that we have on the canvas at the moment. I just need the data structure, essentially. And I'm going to loop through these pixels one by one, and I'm going to write on top of this image data the values that we currently have. So to do that, I'm going to consider just this alpha value. Others will be 0 for red, green, and blue. So starting at the ith times 4 index, because they come in group of 4, I'm going to set the image data at the start index to 0. So this is for red now, and this has to be copied 3 more times here. And now we're going to set the green and the blue and the alpha component. This is not 0. This will be the alpha that we calculated previously. And now we put this new image data on the context. So put image data 0, 0. And I don't think I need this complexity value appearing anywhere here when debugging. I know the number of pixels is calculated correctly already. Let's regenerate the data. Okay, this is done. And now let's extract the features. We can see how this progress indicator works now. Much slower when we're dealing with these pixel values. Okay, and now let's run the evaluation. And done. A little bit improvement from previously, but not much. And this is what we get. The images are now stretching all over the canvas there. And I kind of like this view because now we can see the drawings much better, even for those who made small images. They are stretched here like that, but remember that all we do with these stretched images here are counting the pixels as a kind of complexity measure. All the other calculations still happen the same on the raw point data. One thing I am really curious to see is Herminio's house. Aha. It was like that. For some reason, the app registered some point very, very far away, and that's why its width is so huge. Now let's try drawing here, and I do sense a little bit slower reaction time here, because every time we make a new update to the drawing, it's going to take the features, including this pixel feature, which is slower to calculate, and basically it takes a little bit longer time here. I would say it's still real time.